A new age of discovery is dawning in the distillery of space. Unlike before, the telescope is ready to reveal the secrets of the universe. What secrets does it reveal? How does this change our perception of space? Join us as we embark on a journey with the James Webb Space Telescope. It is a marvel of human wisdom that promises to change our view of heaven forever. The journey of the James Webb Space Telescope, JWST, began in 1996 when it was first proposed as a successor to the Hubble Space Telescope. This proposal arose out of a desire to go deeper into the universe and explore dimensions beyond Hubble's capabilities. The goal of JWST was to solve fundamental questions about the origins of stars, galaxies, and planetary systems, and to provide unprecedented insights into the cosmos. Initial discussions about the design and mission goals of the telescope involved scientists, engineers, and space agencies from around the world. Those initial stages were characterized by discussions and reflections on the technical feasibility of such an ambitious project. The vision was clear: to build a telescope that could observe the universe in the infrared spectrum, allowing it to see through cosmic dust clouds and look into the most distant regions of the universe. By 1997, after extensive feasibility studies and discussions, 3 groups of public and private experts were formed to evaluate the feasibility of building the JWST. These teams worked independently to evaluate various aspects of the project, including technical requirements, potential challenges, and estimated costs. Their common conclusion was positive: a telescope could indeed be built. This was an important milestone that took the project to the next stage of development. NASA recognized the potential scientific successes of JWST and agreed to fund additional studies to refine technical and economic plans. These studies became decisive in defining the technical data of the telescope, the mission objectives, and the means necessary for development. By 2002, NASA had selected the teams responsible for building critical parts of the telescope and assembled an advisory group of scientists to guide the process. This group played a key role in ensuring that the telescope met its ambitious scientific goals. That same year, the telescope was officially named the James Webb Space Telescope in honor of James E. Webb, a NASA administrator during the Apollo era. Webb helped lead NASA in its formative years, overseeing the development of the Apollo program and supporting space science research. Naming the telescope after him was a fitting tribute to his contribution to space exploration. Building the JWST was an enormous task that required the development of new technologies and methods. Unlike the Hubble Space Telescope, which could be maintained and updated by astronauts in orbit, JWST was supposed to function perfectly from a much greater distance, beyond the reach of human intervention. This meant that every component had to be carefully designed, built, and tested to ensure its reliability and performance in harsh space environments. JWST's primary mirror, consisting of 18 hexagonal segments, was one of the most critical and complex components to develop. Each segment had to be precisely shaped and covered with a thin layer of gold to improve its reflection in the infrared spectrum. These mirrors were then mounted on a complex backplate structure that could adjust its position with nanometer precision. The goal was to create a uniform, seamless reflective surface capable of capturing the faint light of distant celestial bodies. Developing the telescope's sunshade was another major technical challenge. The sunshield, which consisted of 5 very thin layers of specially designed material, was supposed to protect the telescope from the intense heat of the sun, keeping the instruments at very low temperatures. This heat shield was necessary for the telescope to function properly in space. The sunshade design and mounting mechanisms were extensively tested to ensure that they functioned properly while the telescope was in orbit. In 2012 to 2013, various parts of the telescope were built in various parts of the world. NASA, the European Space Agency, ESA, the Canadian Space Agency, CSA, and many industrial partners participated in the project collaboration. Each component has undergone rigorous testing and validation to ensure it meets the high demands of spaceflight. JWST was assembled and tested at NASA's Johnson Space Center in Houston, Texas. Here, the fully assembled telescope underwent a final series of environmental tests in a massive thermal vacuum chamber. These tests simulated the extreme conditions of space, including the vacuum and temperature fluctuations of the telescope. This final round of testing was crucial to confirm the telescope's readiness for its mission. The long-awaited launch of the James Webb Space Telescope took place on December 25, 2021 at 7:20 a.m. EST. The launch was a major event watched by scientists, engineers, and space enthusiasts from around the world. The telescope was launched into space by an Ariane 5 rocket launched from the Guyana Space Center in French Guiana. The successful launch marked the beginning of the telescope's journey to work nearly 1,000,000 miles from Earth. The journey to the final destination, the second Lagrange point, L2, involved a complex sequence of steps and precise movements. After launch, the telescope's solar panel was deployed, followed on the third day by 2 special pallets containing critical sun shields. These solar shields were necessary to maintain the telescope's operating temperature, and their deployment required careful coordination and precision. On the 4th day, the tower assembly containing the pill package was moved to its final position. Later steps included the introduction of a speed flap which stabilized the telescope by diverting solar pressure onto the sunshade, and the release of the sunshade to reveal the 5-layer sunshade. The deployment of the secondary mirror and its support structure on day 10 and the extension of the wings of the primary mirror on day 13 marked the final steps in converting the telescope to its full operational form. All these stages of deployment were closely monitored by mission management, and measures were planned to address potential problems. The successful completion of these steps was a testament to the careful planning and engineering that went into designing and building the telescope. The James Webb Space Telescope is designed to observe the universe in infrared light, which distinguishes it from its predecessors. This ability allows the telescope to peer through cosmic dust and gas, revealing celestial bodies and phenomena that would otherwise remain hidden. Infrared light is particularly useful for studying objects that are too cold or faint to see with visible light telescopes. These include newly formed stars, distant galaxies, and planets in their early stages of development. By capturing infrared light, JWST can provide detailed images and information about these objects, greatly improving our understanding of the universe. One of the most remarkable aspects of JWST is its ability to look back in time. Because light takes time to travel the vast distances of space, observing distant galaxies allows scientists to see them as they were billions of years ago. This feature allows astronomers to study the early history of galaxies and shed light on their formation and evolution. The telescope's 18-hexagonal segment primary mirror is designed to capture and focus light with unprecedented precision. Each segment can be adjusted independently, allowing the telescope to achieve perfect alignment and produce high-resolution images. This degree of accuracy is critical when observing bright and distant objects, as even the slightest deviation can compromise data quality. JWST's infrared capability also makes it an invaluable tool for studying stars, the dense clouds of gas and dust where stars form. These regions are opaque to visible light, making them difficult to observe with conventional telescopes. However, infrared light can penetrate these clouds, allowing JWST to provide unprecedented insight into star formation processes. One of the telescope's main instruments, the Near-Infrared Camera, NIRCam, led by University of Arizona principal investigator Dr. Marcia Rica, is designed specifically to take these images. NIRCam's sensitivity to red and infrared light allows it to see through dust and gas, providing insight into the early stages of star formation. The camera's high-resolution imaging capabilities allow researchers to study the structure and dynamics of these stellar nurseries in detailed. In addition to studying star formation, JWST is also equipped to study the properties of galaxies. Developed by the European Space Agency, the telescope's near-infrared spectrograph, NIR-SPEC, allows astronomers to analyze light from galaxies to determine their chemical composition, star formation rate, and other important properties. By studying a large sample of galaxies at different stages of their evolution, scientists can build a complete picture of the formation and evolution of galaxies over time. JWST's ability to study black holes is another exciting part of its mission. Although black holes themselves do not emit light, their existence can be inferred from their effect on their environment. The telescope's infrared instruments can observe the cooler gas and stars orbiting black holes, providing valuable information about these enigmatic objects and the extreme physical conditions in their vicinity. The telescope's mid-infrared instrument, MIRI, developed in collaboration with the European Space Agency and NASA's Jet Propulsion Laboratory, is particularly suited to studying black holes. MIRI's high sensitivity to mid-infrared light makes it possible to detect dust and gas near black holes heated by intense gravitational forces. This instrument can also study the outflows and jets associated with the cores of active galaxies, providing information about the powerful processes in these regions. One of the most promising areas of JWST research is the study of exoplanets orbiting stars outside our solar system. Finding and characterizing exoplanets is difficult because of their small size and the overwhelming luminosity of their host stars. But JWST's advanced instruments can detect the faint signatures of these distant worlds. Scientists can determine the size, mass, and atmospheric composition of a planet by analyzing the light that passes through the atmosphere of an exoplanet as it passes through its host star. This technique, called transmission spectroscopy, is particularly useful for detecting potential signs of habitability, such as water vapor. JWST's ability to detect smaller Earth-sized exoplanets is a significant improvement over previous telescopes. Its high sensitivity and resolution allow it to observe a wider range of planets, including those more similar in size and composition to Earth. The telescope's near-infrared camera and slitless spectrograph, NIRIS, developed by the Canadian Space Agency, plays a vital role in the study of exoplanets. NIRIS is designed to study the atmospheres of exoplanets by capturing the spectra of starlight passing through them. By analyzing these spectra, scientists can identify the chemical components of the atmosphere and look for possible biosignatures. In addition to transition spectroscopy, JWST's coronagraphy instrument, part of NIRCam, enables direct imaging of exoplanets. The coronagraph blocks the light of the host star, allowing the faint light of the exoplanet to be detected. This technique is particularly useful for studying the physical and atmospheric properties of exoplanets that are too far from their host stars to be detected by transit methods. The contributions of the James Webb Space Telescope extend to the study of distant galaxies, stars, and exoplanets. Its observations provide important information for understanding the formation and evolution of our own solar system. By studying the composition and behavior of other planetary systems, scientists gain insight into the processes that shaped our own planetary environment. Telescope observations of the outer planets of our solar system, their moons, and other small bodies help scientists understand the conditions and processes that led to the formation of these objects. JWST's ability to detect and analyze the infrared light emitted by these bodies provides detailed information about their composition and thermal properties. This information is valuable for understanding the history and dynamics of our solar system. In addition, JWST's ability to detect infrared light has practical applications on Earth. Infrared technology is used in many fields, such as environmental monitoring, medical imaging, and telecommunications. Advances in the development of JWST's instruments and technologies are likely to benefit those fields, leading to further inventions and improvements. The structure and operation of the telescope also provides valuable lessons about project management, international cooperation, and the development of cutting-edge technology. JWST is an example of what can be achieved when countries and organizations work together towards a common goal. The knowledge and experience gained from this project will be useful for future space missions and scientific endeavors. The James Webb Space Telescope represents a monumental achievement in human exploration and scientific discovery. Its ability to see further into space and back in time than any previous telescope offers unparalleled opportunities to understand the origin and evolution of the universe. From the birth of stars to the possibility of life on distant planets, JWST is poised to transform our knowledge of space.